Boolean algebra will going to deals with a Boolean or a binary variables and this logic operation. So when all the input signals are 1 or high, then the output is 1. Otherwise, the output will be 0. If my input is 0, output will be 1. If my input is 1, then the output will be 0. That's why we are calling it as a inverter gate. But it will going to take only one input signal and produces only one output signal. Hello everybody, a warm welcome to one and all. Welcome back to the session 9 of Unit 1 in the B.Ca's first semester, subject called Fundamentals of Computers. I'm Rohini TS, Department of Computer Science, Vidhyaashram, first grade college, the Temple of Excellence, MYSURU. So before getting into our today's session, we'll just have a recap of our previous session. As we know that in the last session of this unit, we had a discussion regarding the conversion, that's of conversion from octal to hexadecimal, then hexadecimal to octal, and also I have discussed regarding this computer codes. In order to represent the character in the terms of numbers, we are going to use this computer codes, and it will going to include ASCII code, Unicode, and also we have a BCD, EBCDIC, and also we had a discussion regarding the gray code. So that is what comes under computer codes. Today we'll start with a new concept that's all regarding Boolean algebra. So we'll see what do you mean by this Boolean algebra and what are the different operators we have in a Boolean algebra along with a truth table. What is this truth table? Why we require everything that I will be discussing in my today's session. Let me get into it. First we'll see what do you mean by this Boolean algebra. So here Boolean algebra mainly will going to deals with the binary variables. Then what do you mean by binary variables here? It consists of ones and zeros. It has only deals with the two values, that is ones and zeros, and logic operation. That operation will going to be AND operation, OR operation, NOT operation. So for that we have a AND operator, OR operator, NOT operator respectively. So this Boolean algebra will going to deals with a Boolean or a binary variables and this logic operation. And if you consider a standard Boolean expression is what? Combination of what? Operands as well as operator. So when we have that standard Boolean expression here, the input and the output information of any logic gate or circuit can be plotted into standard Boolean algebra truth table. So here with the help of this truth table, we are representing the standard of this logic gate and circuit. Where computer can understand zeros and ones, we are representing it within the terms of digital electronic pulses. That is what zeros and ones. So for that we are going to use logic gate and circuit that can be represented in the standard format with the help of this truth table. So that truth table is what? It is just a visual representation of the switching function of the system. Switching function of the system in the sense whether it is on or off. If it is 0, it is off. If it is 1, then it is on. That's why we are calling Boolean algebra as a switching algebra also. We are calling this Boolean algebra as switching algebra. Why? Because it will going to deals with the electrical pulses, that is zeros and ones. Fine. Then the table used to represent the Boolean expression of a logic gate function is considered as a truth table. Then what do you mean by truth table here? Why? Because we are learning the Boolean algebra or Boolean operator with the truth table that you what have in your syllabus. Then it is necessary to understand what do you mean by truth table. So here it is a representation of a Boolean expression of a logic circuit or a logic gate. So we have a logic gate that will going to perform some of the operation. So here we have a logic gate. So for this logic gate, we are representing the Boolean expression of that logic gate with some table. Then we are calling that kind of table as a truth table here. The logic gate truth table shows each possible input combination to the gate or circuit with the resultant output, which is depending upon the combination of these input. So in this truth table, what it will going to shows? It will shows what is the combination of input. For that input, what we are getting as a resultant or output. That is what we are showcasing here in the truth table. We'll see what are the different Boolean operators we have. So in it includes AND operator, or, not, NAND, NOR, XOR, and we have a XNOR operator. So these are the different Boolean operators. So in further slides, we're going to discuss each Boolean operator and its procedure, how it will work along with a truth table and its logical symbol. We'll see the first one. That's all regarding AND gate. So here the input can be a combination of 3 input, or it can be 2 input. So moreover, we are focusing on the 2 input. So that's why Boolean algebra truth tables for 2 input AND gate. So my concern is regarding AND gate here. Then what do you mean by AND gate? How it will going to work? So all these logic gates is going to deals only with the zeros and ones. So when it comes to the AND gate, it will going to take 2 or more input signal but produces only one output signal. It is taking 2 or more input signal but producing only one output signal. Then what will be the input and output signal? It's always only zeros and ones. That will be based on the type of gate or based on the type of operator that we are using here. So when all the input signals are 1 or high, then the output is 1. Otherwise, the output will be 0. Mainly this AND operator will going to deal with a multiplication. So 0 into 0, 0, 0 into 1, 0, 0 into 1, or 1 into 0 is 0. 1 into 1 only will be 1. That is why when all the input signals are high or 1, then only the output will be 1. Otherwise, if any one of the input signal is 0, then the output will be 0. So you can see the logical symbol and truth table for this AND gate. How we are going to write the AND gate? I am taking 2 input. Let me consider the first input as X and next input as Y. So these are my inputs. AND gate. What is the last character? That is D. Okay. Write in the symbol of D. So this is only apply for AND gate. That is for your reference. I am giving a hint in order to remember the symbol. And in the sense at last D we have, write the symbol as D. Okay. So don't try to apply it for all the gates. So for your reference I am giving here X and Y. As I told earlier, it will going to take 2 or more input signal, but it produces only one output signal. This is output signal. These are all input signal. This is output signal. This is what? AND gate. Okay. Then what is the resultant we are going to get? As I said earlier, it will deals with multiplication. That is what? Product. So let me consider the resultant as F. F is equal to X dot Y. X dot Y. That dot operator represent multiplication symbol or a product. So here you can see the truth table. My inputs are 00, 11, 0, 1, 0, 1. So 0 into 0, 0. 0 into 1, 0. 1 into 0, 0. 1 into 1 is 1. Okay. Only when the inputs or all the inputs are 1 or high, then the output will be high. Otherwise, if any one of the input is low, then the output is also going to be low. This is how we are to remember AND gate. Then what about the OR gate or OR operator here? So this is what? Addition. It will going to deals with addition operation or a logical operation. It is also going to take 2 or more input signal but produces only one output signal. Then when we are going to get 1 in the addition, if any one of the input signal is high, then the output is also going to be higher. If any one of the input signal is high or 1, then the output is 1 or high. So if both the input signals are low, then only the output will be low. Then how we are going to write this OR gate? First, let me consider this as X and this is my Y. So we are going to use this symbol in order to represent the OR gate. So if X and Y are the input, then what will be the output? X plus Y. Let me store it in F variable. X plus Y. By adding, we are going to get this OR gate. Okay. Then how will be the truth table for it? Again, I am taking 2 input. If it is 2 power 2, if my input is 2 power 2, then it will be a combination of 4. That's why we are going to have a 4 combination here. If I am dealing with 3 input OR gate, at that time 2 power 3, I am going to get 8 combination. That is 4 zeros, 4 ones, 00, 11, 00, 11, here 01, 01, 01, 01. But I am dealing with only 2 input here. That's why this is 00, 11, 01, 01. Okay. 0 plus 0, 0. 0 plus 1, 1. 1 plus 0, 1. 1 plus 1, 2, right? That is in the mathematics, but in the computer science 1 plus 1 is 1 here. Why? Because it is only going to deal with only zeros and ones. So here only clearly says that when the input signals are low, at that time when all the input signals are low, then the output will be low or 0. If any one of the input signal is high, that means 1, at that time the output will be 1. Okay, this is OR gate. Then what about NOT gate? Not, that is what? Inverter. If I say yes, then it will say no. If I say no, then it will say yes. That is what? If my input is 0, output will be 1. If my input is 1, then the output will be 0. That's why we are calling it as a inverter gate. But it will going to take only one input signal and produces only one output signal. And then the output state is always opposite to the input state. As I told earlier, if I say yes, it will say no. If my input is 0, the output will be 1. That's why we are calling this NOT gate as a inverter gate, because the output is not at all same as the input. Then how many input it will take? 1, and it produces only one output. So here you can see that this is my input X, and this symbol we are going to use. So this bubble will going to shows that this is invert. That is what? It is what opposite to the input. So if it is X is my input, then X complement or X bar is my output. This is what logical symbol. And how will be the truth table? Only we have two possibilities. X is the input here and X bar is the output. So here we have only two combination. Why? Because 2 power 1. Why? Because it is taking only one input. 2 power 1 in the sense 2. So only two combination we can have, that is 0 and 1. If my input is 0, output is 1. If my input is 1, the output will be 0. That's why we are calling it as a inverter gate. So these are all what? Basic gate. So in the basic gate, we have OR, and then NOT. Okay, so these three comes under basic gate. Next we'll see about the universal gate. Why? Because by making use of a basic gate, we can create some more gates. That is what? Universal gate. So here you can see that next we have a NAND gate here. This is also dealing with two input signals, NAND. Already you know about AND, and also you know about NOT. AND is what? Multiply or a product, and NOT is what? Just opposite to the input value that we are giving. If I am combining both, then it will become a NAND gate. So NAND is what? It's a NOT gate plus AND gate, or AND gate plus NOT gate will going to give us NAND gate. So here you can see that this is also going to take two or more input signal but produces only one output signal. And also it is a complement of AND gate. So if AND gate is A dot B, this is AND gate. Then what about NAND gate? A dot B whole bar, or complement of A dot B become NAND gate. So that the output of NAND gate will be 0 only when all the input signals are 1, and the output will be 1 if any one of the input signal represents a 0. Let me consider I have a two input called X and Y. Okay, so X dot Y is my AND gate, and inverse of it is X dot Y complement, that is NAND gate. Let me consider 0 0 1 1 0 1 0 1. Let's do the multiplication here. So 0 into 0 0, 0 into 1 0, 1 into 0 0, 1 into 1 1. So if it is complemented, then it will just inverse of that. If it is 0, it will become 1. If it is 0, 1. If it is 0, 1, and it will be 0. This is what? NAND gate. Then you can see here the output will be 0 when all the input signals are 1. So here you can see all the input signals are 1 here. That's why the output is 0. And output will be 1 if any one of the input signal is 0. So here this is 0, this is 0, this is 0. That's why the output signal is 1. This is just a reverse of AND gate. Then how we are going to write? For AND gate, we know that in this way we are going to write. If XY is my input, then the output will be what? X dot Y. If it is NAND gate, or if it is inverse or complement of AND gate, then we are going to have a bubble here. Then it will become X dot Y whole bar. That is what? X dot Y complement. So this is one of the way, and in another way also we can write. Let me consider X and Y as my input. This is my AND gate. Fine. This is my AND gate. I will combine this with a NOT gate. Then it will be a NAND gate. Then x dot y will be the output for this AND gate. If I invert it, then it becomes x dot y whole bar. This is regarding NAND gate. Next we'll see about the NOR gate. If I say NOR, then you will be able to understand this is a complement of OR gate. This is also will going to take 2 or more input signal but produces only one output signal. This NOR gate is a complement of OR gate. So x plus y we have in OR gate. X plus y complement or x plus y whole bar is the NOR gate. So the output of NOR gate will be 1 only when all the inputs are 0, and the output will be 0 if any one of the input is 1. Then how we are going to write it? We'll see here. First, let me consider 2 input signal x and y, and x plus y is the OR gate product or OR gate output. X plus y whole bar is the NOR gate. So here let me consider the input values 0 0 1 1 and here 0 1 0 1. X plus y in the sense I need to add it. 0 plus 0 0, 0 plus 1 1, 1 plus 0 1, 1 plus 1 1. Then if I complement it, 0 becomes 1 and 1 becomes 0. That is what 0 0 1 0 0. You can see here the output will be 1 when all the inputs are 0. Here you can see we have 0 and 0 for x and y. Then the output will be 0. Then when any one of the input signal is 1. So here we have 1, 1 and 1. That's why the output is 0. Then how we are going to write this NOR gate? This is what the representation of OR. Fine. X and y. This is OR gate. This is what NOR gate. That's why it will going to have a bubble. Then it become x plus y whole bar. If this is what consisting of OR gate with a bubble or inverter, then we are calling it as x plus y whole bar. That represents the NOR gate. And also in another way, how can we write? First I am just going to write OR gate. Then I will add it with a NOT gate. Then it will become a NOR gate. So here x, y, this become x plus y. If my x plus y is an input for NOT gate, then it will become x plus y whole bar. As we given for x to xy or x complement, same way x plus y is my input and then it become x plus y whole bar. Now we are calling it as what? NOR gate. Okay, fine. This is all what? Universal gate. And also next what we have? XOR. XOR, that is exclusive OR gate. Then how we are going to represent it, how it will going to work, we'll see. Here also it will consist of 2 or more input signal but produces only one output signal, and also it is a different form of OR gate. So we know about OR gate, x plus y or a plus b, any variables you can take based on the input. So this is what different version of OR gate. Then how it works, it produces the output 1 for only those input combinations that have odd number of ones. So when I have odd number of ones, then the output will be 1. So then the output will be 0 if there are even number of ones. So if I have even number of ones, that is 1 1, x and y value is 1 1. I have 2 ones here, that is even number of ones we have. That's time the output will going to be 0. So the output is 1 if there are odd number of ones. Then the output will be 0 if we have even number of ones. And how we are going to represent this XOR? For OR we have to use plus. If it is exclusive OR, then plus is surrounded by circle, then we are calling that as a XOR. Here you can see the symbol here. So in this way we are going to represent. We'll see the symbol and truth table here. So for OR gate, we are simply going to write like this, isn't it? If it is exclusive or it is a different version of OR, then we are going to use this kind of method in order to represent the XOR. So here x and y are my input and the output will be x or y. Then here you can see the truth table here 0 0 1 1 0 1 0 1. So here I have a even number of zeros, then it will be 0. Here I have odd number of 1, that's why output will be 1. Here also I have odd number of 1, that's why output is 1. Here I have even number of ones. So then the output will be 0. Okay. This is all regarding XOR. What if I am going to add NOT gate to it? Then it become XNOR. So this is what? Just a complement of XOR gate. This XNOR, exclusive NOR gate. It's the inverse or a complement of this XOR gate. Then what kind of output it will going to produce? The output of XNOR is 1. So when both the input signals are same, whether it can be 0, 0, 1, 1, whatever it is, if both the input signals of X and Y is same, whether it can be equal to 1 or 0, then the output will be 1. So the output will be 0 when its inputs are different. If it is like 1, 0, 0, 1, so then the output will be 0 if the inputs are different, like 0, 1, 1, 0, those two are the combination. Then how we are going to represent this XNOR? Then we are going to have the product, then that is surrounded by circle. Then that is going to represent this XNOR. Then how will be the symbol for this? If I am not writing this bubble or inverter, then that will be XOR. If I have a inverter, wherever you are going to get N in the words or in the gates, then we have a inverter there. That's why it's a complement of XOR. So in this way, I am going to write the XOR. So if I am inverting bubble or inverter to it, then it become XNOR. Okay. So F is equal to XNOR Y. Then how will be the truth table for it? So if I have a same number of zeros and ones, or if my both the inputs are same, then the output will be 1. So if any one of the inputs are different, then the output will be 0. Here also it will be 0. Here 1 and 1. In both the inputs are same. That's why it will be 1. Here also both the inputs are same. That's why the output will be 1. Okay. This is how we are going to write the truth table for all the logic gate with a symbol. I hope you all understood regarding this. In my coming session, we're going to see about the different types of software, and also we're going to learn about this computer languages. What are the different computer languages we have? That I will be discussing in my coming session. Until that, keep learning, keep on growing. Thank you.